Welcome to the technical sessions segment of the 2020 ISS Research and Development Conference. My name is Alan DeLuna. I'm the Executive Vice President of the American Astronautical Society. I'd like to introduce Jim Way. Jim is the Executive Director of the American Astronautical Society. AAS is a nonprofit technical society founded in 1954. Our mission is to advance all space science and exploration activities. We do that through our well-known symposia, like the Goddess Symposia.
Sarah, you can stop the screen share.
Okay, back to it. We're a nonprofit and we do a number of symposia. We do the Goddess Symposium, the Glenn Symposium, and the Von Braun Symposium. The Von Braun is coming up in a few weeks, about 4 weeks, October 26th through the 28th. We also have some technical conferences like the Astrodynamics Specialist Conference, our Spaceflight Mechanics Meeting, and our Guidance, Navigation, and Control Conference. You can find out all about all of our symposia and technical conferences on our website at astronautical.org. We also partner with folks like CASIS, the ISS National Labs, on this conference, and we lead the effort on these technical sessions we're starting today. Make sure you follow us online. You'll see there's lots of interesting and informative information on our websites. I'd like to thank our sponsors. First, our platinum sponsor, Boeing, who has been the lead sponsor of this event since it started back in 2012. And thanks to our silver sponsors, Jacobs, KBR, Leidos, Oceaneering, Teledyne Brown Engineering, and the Engineering and Innovative Technology Development Organization of the University of Alabama at Birmingham. Today we have 6 sessions. Now, between each session, we'll be taking a 15-minute break and a 45-minute break before noon. And we wrap up at 8:45 UTC, Universal Time, or 4:45 Eastern Time. So to do Q&A, if you have questions for the panelists, go ahead and click the little Q&A button down at the bottom and type in your question. Make it short enough so that we're able to read it. The session chair is able to read it. And if it's decided to be asked, the question will be asked by the session chair. As I said, we're doing UTC times today. That's because we're in multiple time zones around the world. This is just an example. For UTC, if you want to get to Eastern Daylight Time, subtract 4 hours. If you want to get to Central Daylight Time, subtract 5 hours. And if you want to get to Japanese Standard Time, and we have some folks from Japan in, you add 9 hours. Now, if you need the full agenda, it's available at our issconference.org/agenda. Now, today's presentations, or today's session, the first one is chemistry and particle physics research capabilities. Our session chair is Kenneth A. Savin. He's the Senior Director of In-Space Production at the International Space Station U.S. National Lab. Now we're going to play the 6 different presentations that the authors sent in. I do warn you, we do have one presentation that has no audio. So on the presentation that has no audio, we'll be going through the slides in about 15-second intervals. So if we can go ahead and start the slides, please.
Good morning, this is David Aveline, and I'll spend the next few minutes talking to you a bit about the Cold Atom Lab, in particular highlighting some of the results from our commissioning phase. These were recently published in Nature in the June 11th, 2020 issue. The CAL instrument is a design and build of Jet Propulsion Laboratory, and it was launched to the ISS in May of 2018. For the next 3 months, it had its commissioning phase before launching into a series of science investigations from a multitude of investigators from around the world. In particular, I wanted to show the hardware. In this case, this is a the main part of the instrument that occupies a quad locker, or 4 of the lockers of an ISS express rack. This is also an exploded view, already showing some of the drawers coming forward out of the system that carry the lasers or the control electronics. Also pictured on the side is the science module. In particular, the science module was upgraded in February of 2020 to include an atom interferometer. The science module itself is surrounded by 2 layers of magnetic shielding, and all of this is to keep the fields low within the vacuum chamber, which is at the heart of the system. The chamber itself has 2 sides to it. One is a source cell at about 10 to the minus 8 torr, and then there's a ultra high vacuum chamber where we can get much longer lifetimes of the cold atoms. At the ceiling of this system is an atom chip, and this is where very, very tight magnetic traps can be formed. We can hold the atoms in there, and we can apply radio frequencies to do an evaporative cooling process where we remove the hottest atoms and leave behind colder and colder gases. The beam layout here, shown on the left hand side of this picture, allows me to describe how there's a 2-dimensional magneto-optical trap in the lower left. This is in the source cell. We cool them in 2 dimensions and allow the 3rd dimension to be free. This produces a cold atom beam that can travel up to the science chamber through a small aperture. The 2D Mott push beam that we show at the bottom there is directed straight up the path. This improves the flux. It also serves as a imaging path for a through-chip imaging path. The 3-dimensional Mott is formed in that science chamber about 15 millimeters below the atom chip surface. We also have an imaging axis parallel with the atom chip. The way we look at the atoms in Cal is a method called absorptive imaging. We shine a very brief flash of resonant laser light through the cloud, and the shadow it casts on a camera is what tells us about the position, distribution of density of the atoms, and the momentum. What you see on the far left is the same experimental sequence carried out on the ground before launch versus on orbit. In the upper left, we see a very typical bimodal distribution, with the central core being the cold BEC, and surrounding it fits very well to a Gaussian, is a thermal cloud. On orbit, we also see the BEC formed in the middle, but in total, we saw a 3-fold increase in atom number. These atoms, it turns out, are the non-magnetic state of the atoms. By applying a variety of magnetic fields, we can separate out the 3 different internal states. And what we learn is, on the ground, when there is gravity applied, while we are evaporatively cooling, these non-magnetic atoms fall away naturally and aren't trapped by the fields around them because they are generally not magnetic. In space, they are able to hover around longer and are very weakly confined by the magnetic field. On the far right, we can see an example of this. They're slightly responsive to very high gradients and large fields. Once we have full control of them, we can apply decompression, so very slow adiabatic decompression, and then put the atoms all into that non-magnetic state. This allowed us to get to very long free expansion times and extremely cold temperatures, sub-nanokelvin. With routine production of BECs, Cal was ready for its science phase, where a variety of PIs are studying a range of topics. 3 of those are covered in this ISS conference. Thank you.
Hi, my name is Matteo. Together with Shengwei, Jim, and under the supervision of Nan Yu, we work at the Jet Propulsion Laboratory in Pasadena, California. My talk is called Blue-Detuned Box Potentials for Spaceborne Quantum Gas Experiments. Before I define each of these terms, let me first mention the mission that this work was performed towards. It is called BCAL. It's a collaboration between NASA and the German Space Agency, DLR, scheduled to be launched in 2025. BECL stands for Bose-Einstein Condensate and Cold Atom Laboratory, where a Bose-Einstein condensate is a new state of matter that occurs at very low temperatures, around nanokelvins, that is just a billionth of a degree above absolute zero. Now, the intrigue in this phase is that it is purely governed by quantum mechanics, so it's a purely quantum state of matter, and will employ atoms belonging to this phase to perform our quantum gas experiments described in the talk. BECL is actually a follow-on mission to CAL, the Cold Atom Laboratory, that is already on the ISS and has already been successfully generating and manipulating cold atomic gases on the International Space Station for the last 2 years. Of course, being a follow-on mission, BECL will comprise additional features, among which the ability to place cold atoms in an optical Blue-Detuned box potential, such as the one showed pictorially on the right. These potentials are optical, that is made by light. Light whose frequency is Blue-Detuned, meaning that it will cause a repulsive force for the atoms. So the atoms will be repelled by the walls, and they will sit in a dark region, in a dark enclosure, hence the word box potential. Now, with the ability to shape light in arbitrary forms, which I will talk more about in a minute, but in this example, for example, you see a tube and 2 sheets. By then tuning the shape of light in arbitrary ways, you can make the atoms adapt to whatever geometry you would like. So essentially you have your quantum gas, and you can make it evolve and sit in an arbitrary geometry, arbitrary system. Why you would like that is so that you can perform quantum simulation experiments. Now, quantum mechanics is actually too hard computationally for classical computers. You cannot physically solve a large quantum system. That is because of the rules of quantum mechanics and of the complexity that they entail, which of course is limiting us in today's world, because we would like to engineer quantum materials such as superconductors, so we would like to understand the behavior of large quantum systems, but unfortunately we cannot rely on classical computers to perform this computation. A possible workaround is the so-called quantum simulation, that is to use a distinct quantum system to simulate my quantum system of interest. For example, I want to understand conduction of electrons in a solid, let's say. So what I do, I build an analogous system with cold atoms in a potential made by light, so in a box potential that mimics the geometry of my potential of interest. And then I just observe the evolution of the atoms in this potential, and that will give me a real-time solution to the equation of motion. We want to perform these experiments on the International Space Station because performing them on Earth causes all sorts of problems. Gravity causes sagging to the bottom. All atoms in any potential, they will not just respond to the potential that we shape with light, but they will also experience gravity, so they will always fall at the bottom and sag at the bottom. Gravity affects different atomic species depending on their mass, so this causes a spatial separation if you're using mixtures, and limits the kind of experiments you can do in that situation. Also, gravity causes free fall of the atoms, which means that it sets an upper limit to the duration of any experiment that you can possibly do. Hence why we would like to perform these experiments in microgravity, because taking gravity out of the picture is the most elegant solution to all these problems. Now, to actually shape light in these arbitrary potentials, we demonstrated the use of a device called a spatial light modulator, just to give you some examples. These are actually pictures taken with a camera of the resulting light distribution. Here's an expanding box. Here's a partition that is raised in a box, a barrier with a slit, and then just to emphasize the arbitrary and freedom of the patterns, here's a dog made of light, and here's light that is everywhere apart from the dog outline. With that, I conclude. Thanks for the attention.
Hi, everyone. It's Jim Way, just letting you know that these slides have no recorded narration, so we'll be advancing them every 15, 20 seconds or so you get a good chance to read them, but it'll be quiet for the next few minutes. Thanks.
This is Cass Sackett. I'll be summarizing my talk, Quasi-Adiabatic State Preparation of Ultracold Microgravity. The basic idea here is that we're using the CAL apparatus on the ISS to produce ultracold atoms. The atoms are produced in a tightly confining trap that's right close to a surface. We want to use these atoms for atom interferometry, and in order to do that, we have to expand the trap to cool the atoms off and reduce their velocity, and also displace them from the surface so that we can access them with laser beams. And we're trying to do that with quasi-adiabatic, which basically means just a slow expansion. So here's a little diagram of the chip. So the chip is defined by these wire traces. They carry currents IZ and ID, and also by a bias magnetic field with components Bx, By, and Bz. Those produce a harmonic trap with oscillation frequencies and a minimum at a certain place. We can adjust the bias fields and the currents to try to reduce those frequencies and move the trap minimum to where we want. We measure this by taking pictures of the atoms. The little black dots are where the atoms are. It's the shadow of atoms in the laser beam. So we can adjust the trap configuration in a certain way and see where the atoms end up. When we do that, the dots are the measurements and the curves are what we expect. And you see they disagree. When we're expanding the trap, we're trying to do this expansion we want, that the atoms don't seem to follow correctly. In the upper picture, you can see the dots are moving away from the line and actually towards the chip at z = 0. And the frequencies aren't getting as low as we wanted. And that's not so great. We tried to understand why. Another tool that we use to do that is to release the atoms from the trap and observe how they move. So the little part down below shows a little video of this. So there's different time of flights after turning the trap off. One thing you can see is that we get two clouds of atoms. Those are actually atoms that have been put into two different spin states with different magnetic moments, just by the way we turn the trap off. But they also accelerate away, and the acceleration is proportional to the magnetic moment of the state. And so we know that that acceleration is caused by some kind of magnetic field. We model that magnetic field as a background gradient, so a field that's proportional to the position. The G's in that matrix are fit coefficients that describe the gradient, and the x0, y0, z0 here is actually the zero location of this background magnetic field. The x, y, and z are just the actual location. So what we do is we fit both the time of flight trajectory, so the green and the orange curves, and also the trap parameters that we measured, so the black and the blue curves. We fit all that together to try to extract what that background gradient coefficients are, and it worked out pretty well. We got reasonable, but we got surprisingly large numbers. The field 0 is a few millimeters away from the trap, but the gradient components are as big as 10 Gauss per meter. We were expecting gradients more like 1 Gauss per meter, so that's a bit surprising. We were surprised to see that. The source of this big field has not yet been identified. So that's something. The implications, well, despite this background field, we were able to cool the atoms down to a 10 Hertz trap. That's not as cold as we wanted, but nonetheless, the velocities of the atoms in that trap were quite low, and it was in about the right place. So that's actually probably sufficient for the kind of atom interferometry work that we want to do. Temperatures correspond to about 10 nanokelvin, but the condensate atoms themselves that we'd be working with expand pretty slowly at a sort of equivalent temperature of about 200 picokelvin. There are other techniques you could use. The shortcut to adiabaticity is a technique that might work better, and so that's something that actually other groups have explored and looked like it might have some promise to do that. So thanks, and I'll be taking your questions, I guess.
Welcome, and thank you for attending our presentation, MOCHII ISS National Laboratory Portable Spectroscopic Electron Microscope. I'm Chris Owen, CEO of Voxa, and I'm delighted to update you all on progress towards placing microscopic imaging and elemental analysis on ISS, and to share with you how you might be able to use MOCHII onboard ISS for your own microgravity research. While powerful analytical capabilities are available on ISS, many samples cannot be sent back to the lab, are extremely time critical, or evolve or might be destroyed during transit. One example is the 2013 EVA emergency that occurred with Italian astronaut Luca Parmitano, whose EMU suit suddenly started flooding with water during a routine spacewalk. The particles found inside the fan pump separator in his suit were only identified by electron microscopy after the suit was returned to Earth. American spacewalks were suspended immediately following the emergency and only resumed 17 months later. If ISS had electron microscopy on board at the time, the root cause could have been identified and potentially mitigated in days rather than months, allowing a return to full ISS capabilities, including spacewalks much earlier. At Voxa, we developed a new portable imager and spectrometer called MOCHII for unprecedented in-situ diagnostics in science. MOCHII combines the best of both light and electron microscopes in the size of a coffee maker. In particular, it can provide nanostructure and material composition identification by way of SEM imaging and energy dispersive X-ray spectroscopy. MOCHII's coffee maker footprint weighs less than 15 kilograms and consumes less than 100 watts of power. Due to its portability, it mitigates the need to send samples back, is remotely operable via tablets or phones, and fits in the overhead bin of an airplane. MOCHII is just as at home on vehicles, whether on ocean vessels, oil rigs, or even space vehicles, as it is in the lab. We've tested in various environments ranging from undersea habitats, laboratories, and home kitchens, and we're now deploying onto the International Space Station as part of a NASA SBIR Phase 3 commercialization agreement. This will provide powerful new imaging and spectroscopy capabilities for broad use by the microgravity research community on ISS. To provide some background, here is how electron microscopes compare with light microscopes, which most everyone have had experience with. These tools are complementary, each with advantages and disadvantages. Light microscopes, left, have certain drawbacks such as limited resolution, contrast, and depth of focus. They can do depth sectioning due to their weak scattering. Electron microscopes, on the other hand, have advantages of higher resolution, contrast, and greater depth of focus, and due to strong scattering have excellent surface sensitivity. Both provide a form of spectroscopy. In the case of light, they are visible colors that we're all familiar with, and for electrons, the chemical composition is. MOCHII is intended to be used for three main purposes aboard ISS. First, as a diagnostic device supporting crew and vehicle safety. Secondly, it will be made available for public use as a national laboratory facility for microgravity research and engineering. Third, it will serve as a platform for future mission research, including for Moon and Mars. After several years of detailed preparation, MOCHII launched to the ISS on the NG-13 mission in February 2020, aboard the Cygnus space vehicle on top of a Northrop Grumman Antares rocket. This mission carried 7,500 pounds of supplies, food, and experiments, including MOCHII, destined for the ISS. It was an amazing moment for our team to see a system we designed and built lift off the launch pad on a rocket and be propelled into low Earth orbit at 17,500 miles an hour. The Cygnus was captured a few days later after liftoff by flight engineer Drew Morgan and berthed with the ISS shortly after. In fieldwork, impacts to the body from the environment can range from mild to severe. On the Moon, for example, dust is extremely prevalent due to the electrostatic charge, which causes it to cling to fabrics and equipment, which then makes it onto the vehicle after EVA. At NASA Johnson Space Center, health researchers are studying inhalation of simulated lunar dust particles and its effect on the body. The researchers found that not only does dust naturally find its way into the lungs, some amount gets swallowed and makes its way into the gut. These are images of dissected rat intestine, which shows that grains of fine simulated lunar regolith dust, of sizes on the order of micrometers to tens of micrometers, embeds itself into the stomach lining. The composition is distinct, with the larger particles embedding into the convolutions of the intestine, while the finer dust also attaches to the smooth portions. These particles can irritate the linings of tissues and cause deleterious health effects over time. This type of knowledge has impacted the understanding of crew health during exploration and also can aid first responders as well as hazardous fieldwork situations. Electron microscopy is often used for examination of semiconductors and semiconductor packaging and for reverse engineering products. This example is a failure analysis investigation we helped a small business to conduct with MOCHII. During the time of coronavirus, many engineers and researchers cannot get into their facilities to use larger laboratory machines regularly. MOCHII's ability to go anywhere enables work to continue unimpeded, whether at home or at customer sites in the field. In this investigation, a rugged diode used in a high-speed rotary power generator kept failing, throwing off its Kovar cap under a few thousand Gs and damaging the apparatus spinning at very high RPMs. The investigation using MOCHII's spectrum imaging feature indicated copper concentrated at the interface seam, resulting in weakness despite the strong housing components. The likely failure mode was fatigue, exacerbated by a segregation of softer metals to the seam. I hope you've enjoyed this presentation. In closing, Voxa is very excited to serve new analytical needs for both users on the ISS and in the field. Come visit us as projectvoxa.com, and we look forward to conversations with all of you. Thanks very much for listening.
Hello, I'm excited today to talk to you about some of the work we've been doing to develop a platform for flow chemistry on the International Space Station National Lab. I appreciate the opportunity to give this talk and to talk a little bit about the exciting progress we've made over the past. My presentation will talk about our motivations behind developing this platform, really thinking about how to construct and benchmark a flow chemistry platform, establishing safe practices, providing a core facility for other scientists to take advantage of, and demonstrating synthetic processes in an on-demand sense are viable on the lab. This project was a collaboration between the National Lab, and particular Ken Savin, who really championed the concept of doing on-demand chemical reactions and synthesis on the space station. Space Tango, who is our implementation partner, and their amazing team of engineers, and my lab at Boston University. In the talk, I'll talk a little bit about the details of the design concept of the flow chemistry cube lab, going into details around how we designed in specific attributes with the idea of downstream expansion and utilization by hopefully many scientists in the future. And then I'll talk a little bit about some of the chemistry we're doing, some of the experiments that we're working to get done on the station, as well as some of the ones we've already done and the outcome of those experiments. So I hope you'll have an opportunity to take a look at my presentation, and thank you for your time.
All right, thank you for all those briefings. For those of you that missed me just buggering up Kevin's introduction a little while ago, Kenneth A. Savin, I buggered it again. Ken Savin is the Senior Director of In-Space Production for the ISS Space Station U.S. National Lab. So he's going to take over in just a moment, and he's going to manage the Q&A with the different panelists that we had. Now again, reminder, if you have any questions you want to add to the list, go and click the little Q&A box at the bottom of your screen and type in your question. Please, if you can, identify who you want to ask the question to so that Ken has a better idea of who he should direct it at. All right, Ken, we're almost got all your folks online. We've got 2 more to come. You know, I'm supposed to dance, but I don't dance well. There we go. Ken, take it away.
Hi, everyone. Welcome to session 1 of day 1 of the ISS National Lab Research and Development Technical Session. I'm joined today by the panelists, Dr. David Aveline. He's a member of the Cal Science team at the Jet Propulsion Laboratory in beautiful Pasadena, California. Matteo Sbroscia, who is a postdoctoral fellow also at JPL. Makan Mohageg is a quantum technologist at the Jet Propulsion Laboratory. And Cass Sackett, he's an associate professor of physics at the University of Virginia. Christopher Owen is the CEO of Seattle-based Voxa, and Professor Aaron Beeler, who is at Boston University. Again, if you have questions, please submit them. Let's see here. So I've got one question right now coming in dynamically through the audience. So I'm going to go ahead and ask this. This is for Christopher Owen. For the electron microscope, I wondered if the biological samples require metallic staining or coating.
Great question. Some of them do, and probably the majority of them will. And the pressure that we operate at is typical vacuum for tungsten electron sources. And for that reason, there will probably be a need for some coating. So we've provided provisions for that in the form of a metallic coater on orbit, and that will be part of analytical packages if necessary for biological investigations.
So in general, sample prep beyond biologics? Do you need to be doing the coding?
It only depends on whether or not samples are non-conductive or require enhanced contrast. So in general, it's sample specific and will provide the capability depending on the investigation. And that'll be something we'll plan together with users.
Okay. A question for Matteo. How long does this need to be? How long does the duration for these need to be for the simulation to be worthwhile?
So, I mean, you only shine this box potential when you really create a Bose-Einstein condensate. So when you really have finished pretty much like all the cooling process that Cal already does, you take within like 15 and 30 seconds. And then you have the atoms sitting in these box potentials for, I mean, really for however long you want until like the vacuum allows you, like, I mean, before, like, I mean, the atoms kind of like die because of collisions with the vacuum pressure. But usually, like, I mean, typical duration range from like tens of hundreds of microseconds up to like a few seconds. But it really depends on your experiment, on your measurement, and really on how long you can actually hold them. Even in, I mean, actually, one of the advantages of having in space is that like there's no free fall, so the atoms like don't fall down and don't like eventually smash either onto the box potential or onto the vacuum chamber. But there is still a background pressure. There are still collisions with background atoms, which will eventually heat your atoms and make the experiment not worthwhile anymore.
Okay. So Dr. Aveline, along the same lines, how long are we up to now as far as what you're seeing in the lab and what we're seeing on the Cal system on station? How long do we see the BECs lasting? And ultimately, what are we trying to get to?
Sure. So what we're basically seeing so far, we achieved a little bit longer than about 1 second of, we call it like the free expansion time. So basically, we go through some stages. In fact, there's about we'll call it 3 different methods or so to get the atoms very cold to begin with. And we need to get them extremely cold so that they don't spread out so much. I mean, really, that's how we're measuring how cold they get. So the first step is getting them so cold that they at least stick around high enough density, we'll see them much later. And then the other trick is not to have them fly off the screen. We saw a little bit example of that in Cass's slides, or on the ground. Of course, we're limited by the fact that they drop just straight out of view. We were able to get about 1.1 seconds with the results that were in that Nature article. And I think we have there's some techniques going on by some of the some of our PIs that are trying to push for reaching seconds, multiple seconds. So that's kind of the time scale that we're on.
So 1.5 seconds, give or take, is that some kind of a record?
Depending.
Like a world record?
There actually is a world record on the ground with an extremely tall fountain. So basically, if you make your structure large enough, you can in principle get effectively longer times of observation. This is definitely the record in size in the instrument that's yay big, because it got to fall with the atoms, right? It's constantly in orbit. But yeah, we're kind of pushing the boundary. It's also but when Cal was first created or founded, the goal was to get 1 second. It's sort of sometimes it's a moving target, 5 to 6, 7 years later when you get the thing working in space. But yeah, we're close. I think their actual record is around 2 seconds. So it's not like we're an order of magnitude away or something. But they're still working on it.
Okay. Chris, we had another question. Just somebody asked for kind of a comparison for the size of the MOCHII system versus a standard electron microscope.
Sure. I think there's a slide in the main presentation for this if you want to do some comparisons. But in general, ground-based electron microscopes are approximately a ton or two in size, and about the size of they require about the size of a car, more or less. There are smaller ones that are so-called benchtop electron microscopes, and most of those are about the size of a mini fridge, and they have similar capabilities to MOCHII, but most of them are about 200 pounds and much larger. So MOCHII is quite small. It's the size of a coffee maker and can fit in the overhead bin of an airplane, and weighs about 14, 15 kilograms.
Okay. So next question's for Makan. Talk to us a little bit about the concept of long-range teleportation of quantum states and what the applications of that are.
Right. So in the Deep Space Quantum Link program, which is from Science Mission Directorate of NASA, and I'm the PI on, we seek to implement long-range teleportation of photonic and possibly atomic quantum states, not for a technology application, but to test fundamental physics, to see if the foundations of quantum mechanics hold over these long distances where things like gravitational potential energy and even time dilation from relative motion between sender and receiver play a large role. Of particular interest, I think, is this concept of relativistic simultaneity, and coupled with the concept of quantum mechanical measurement, where you make a measurement, you collapse a wave function in quantum mechanics, and things are known from that point on. But you couple that with special relativity, where you have high velocities between two observers, and the observers will observe a different causal sequence of events, depending on their frame of reference. That introduces, I don't want to say a paradox, but at least an ambiguity in the interpretation of the quantum mechanical result. So that long-range teleportation test, it could really address some fundamentals of physics that could give insight into potential relationship or coupling between gravity and quantum mechanics.
Okay, so in your slides, you also talked about space-based quantum connectivity relay, I think is what it was called, but it's a communication system. Could you talk a little bit about that? I know we didn't hear it in the slides. Could you just describe what that is?
Sure, I can describe that one a little. One of the potential, and there was actually a Wired magazine article about this that came out right at the beginning of this COVID nonsense. What it is a space-based entanglement beacon. So this is more like a technology or an infrastructure asset, where we have a source of entangled light in space that in a spacecraft that has two telescopes. So that entangled pair can be split up and transmitted to two different ground receivers or two different arbitrary receivers. And it's engineered in such a way that that transmission is as efficient as possible. And when the entangled photons arrive, they could be used as an information resource to entangle two quantum networks, two terrestrial quantum networks. So through the space-based relay, we can make a network of quantum networks to serve quantum information science needs.
Okay, thank you. Professor Beeler, So how big in your presentations, and I recommend to everybody that you go in if you can and take a look at the full presentations because they were actually really interesting, I thought. You talked about this flow chemistry unit and the size, but you never really talked about the size relative to the same unit you have on the ground. You talked about having a mirror unit, but how does it relate? Is it the same size, or are you making a smaller unit for space?
Sure. So the box that the system that was on the ISS is certainly smaller, just because it needs to be really compact to fit into the cube lab. In terms of the dimensions in our lab, all of the fluidics are all identical. We let it spread out a little bit, just because it makes life a lot easier in terms of manipulation and fixing problems and those sort of things. But in terms of all the volumes and dimensions with regard to the fluidics themselves, everything is identical.
Okay, so with that in mind, are you able to do the same types of chemistry that you do on the ground in this unit space? And we saw what you did. What's coming up next? What should we be looking out for?
Sure. Yeah. In principle, you could. I think the biggest challenge we have in translating chemistry from our lab to the national lab is really around safety considerations when you're thinking about doing chemical reactions in the national lab. So, we just have to make sure that anything that we do try to translate has absolute no possibility of critical failure that could become an issue. In terms of actually being able to do the chemistry, they should be identical. Again, I think the biggest issue is just making sure that we follow proper safety and that we have everything worked out in that regard. And so what do we do? So a lot of the projects that we're looking at moving forward are trying to expand the system, evolve the system to be more of a platform that would allow us to do things like on-demand synthesis of pharmaceuticals, on-demand synthesis of a biologically relevant molecule that someone might need for a biological study on station that, for instance, had a lifetime that was too short to ship, right? So those are things that happen all the time in biology labs terrestrially. So there's some limitation there. So if we could enable on-demand production of those things. We're also looking a lot at how we can utilize microgravity as a variable to manipulate some of the fluid dynamics in a way that we can control the outcome of a chemical reaction in a way that cannot be possible terrestrially. So those are more fundamental exploration compared to more applied applications. But those are two of the areas and two of the types of projects that we're really trying to move forward in the coming years, or year, hopefully.
Okay, thank you. Professor Sackett, I had a couple questions for you, just as you wheel away. So for the quantum or atom interferometer, why space? Why would we want to do this in space? And is it noise related or what have you? And where do you see this leading? Like, where are we going with this?
Sure. Yeah. There's a couple reasons actually why it's interesting to do it in space. So one is that it gets around a big limitation on the ground, which is this free fall problem. So atom interferometry in general benefits from long measurement times. It usually goes quadratically, so you're really pushed to that. But it's, normally you want the atoms to be sort of in free fall. And on the ground then, so if you want a long time, you need a long drop distance, which people have certainly done with these large towers and drop towers and things. That's basically pushing to get very long measurement times. And so naturally enough in space, that's just much easier. Like having to deal with falling atoms and a big drop distance is just a technical headache. And you can only go so far with that. So the hope is that in space, it should just work better because the atoms should more or less sit still once you have them in free fall. So you should be able to do the measurements better in space. So that's one thing, and that's applicable. For instance, people are interested in equivalence principle tests. You compare one type of atom to another. There's reasons to say that you can take advantage of that long time and actually maybe this smaller, well, they're still falling, right? So it's in orbit. So it's not like they're not falling. You can just more easily measure them for a long time. The other thing though, so that's one reason it should just work better, and there's some neat measurements we hope to be able to do. The other reason though is one of the big applications of atom interferometry is inertial navigation. It's very good at measuring accelerations and rotations. And there's lots of efforts to do that on the Earth for terrestrial systems. Navigation is important. But it's particularly important, or could be important in space. Precise navigation in space is not so easy because you don't have GPS or anything to tell you where you are. And star trackers and things, you know, they only have so much signal to noise. So a good inertial measurement system where you're sort of tracking the acceleration and rotation of your craft as it's journeying to, you know, Pluto or some asteroid or whatever, could be an advantage for, you know, improving the precision that you can do that at. So it kind of goes together well, is that the atom interferometry should work better in space, and also there's this kind of fairly important application that if we could make it work well would be, you know, right there sort of ready to use. It's a bit of a road to get there though. I mean, so, you know, there's been a lot of work on the ground to try to do these things. And I think it's probably fair to say the best rotation, well, the best acceleration sensors probably are atom interferometers now on the ground, and rotation sensing is right up there with sort of giant laser interferometers. You know, making those sort of practical and compact and usable in a field system has not been straightforward. But the kind of work that we have to do to put it on the space station and other space-based platforms is exactly the sort of engineering that needs to happen here. So, you know, how far it'll be able to go is tough. There's still some challenges to see, but personally, I think that if there's enough motivation to do it, we could build, say, a navigation system on a space platform that's, you know, better than anything else. You know, that technology could beat any other thing you could think of, I think. So to the extent that, you know, we're willing to keep chasing this for, it'll be a little while yet, but the goal is there. We could really do a better navigation system than anybody else.
Do you see these as being applicable to things like earthquakes and ground observation type systems?
Well, there is, earthquakes is maybe less obvious. It seems, my guess is that a ground-based sensor is probably gonna be better for that. I'm not sure. But there is a big thing, you know, there's these gravity maps people make where they've done this before, where you fly the satellite around and measure gravity and put together geophysical models of what the Earth is and how it's changing. Yeah, in principle, that too could be done better using atoms. So that's a direction too. Yeah. Okay.
So we had a question. I don't know if it was actually targeted at anybody, so I'm gonna put it out there. But the question is, are there relativistic corrections needed for the quantum entanglement studies, or do the velocity and changing momentum vectors of the ISS make up for that? I guess that is the question. Anybody care to address that one? Christopher, did I get that?
I guess since the question is about quantum entanglement, I'll give a first answer. Yeah, you have to take all that into account. Just like the cell phone filters, right? They have to have appropriate bandwidth to accommodate the velocity of a moving car. So too does, you know, we have to accommodate relative motion in all the quantum communication systems. There's and the other question was, does the relative motion of different platforms somehow help cancel out? When you look at the analyses, sometimes you get fortunate, and there's some coincidences that help you, but often not. And generally with optical communication, and including quantum optical communication, when things get good, they get really good, and when they get bad, they get really bad fast.
Okay, that's good. So a number of times there's been discussion of like interaction with astronauts, and the fact that the Cal Lab is on station. There is some astronaut interaction, but it's minimized, and a lot of the studies occur at night, I've been told, well, nighttime for them. So could somebody who's actually using the device tell me a little bit about what the impact of astronaut interaction is and how it's useful? just I'm thinking of from the standpoint of someday, you know, a Cal Lab type system just being an autonomous satellite that has no people and is just running on its own. But for now, you have the benefit of having astronauts there. What is that, if there is a benefit?
Sure. I'll say that a major benefit is that human presence. That number one, when we get the well, I'll start even more fundamental. Because there are humans up there, they've made this interior lab space that is at room temp and very similar to being in the lab on the ground. In fact, it's maybe more controlled in terms of temperature and all the other things they take care of for those. So we get in the same room, and we're benefited from that directly, the fact that that's even there. Second, they're the ones that do the installation for us. So they're the hands-on that'll install it in, hook up the cabling, hook it up to power, connect, you know, different compartments together. And then one of the other major things is if we do upgrades or repairs or troubleshooting. So not that we don't participate with them daily or even monthly, but on a semi-annual basis or so, we've had to do a little bit of troubleshooting or cleaning of optical fibers, for example. And another thing was upgrading the science module. We did this back in February. We actually took an entire part of the system out and plugged in a new one. And that's something that if it was on its own, you know, of course, if it was in its own spacecraft, it's not as easy to get that done. You'd have, I guess, have things be all automated the way it would work. So it does allow us to do these upgrades and those kind of things. In terms of like operation, we try to spend most of the operation time avoiding the exercise activities and other things that would maybe cause more vibrations and so forth. But for the most part, we still overlap a bit with the astronaut active time, and we don't, so far we haven't found any direct consequences. So it's been a very great place to have a cold atom lab, at least for these first couple of years. No bad roommates.
Okay. So another use, I guess, of having astronauts, or another benefit of having astronauts, is avoidance of the free will loophole. I had heard that in one of the talks. I think Makan had actually mentioned that. I was just wondering what that is and why an astronaut is helpful in avoiding that or solving that.
Yeah, great. So whoever asked that question, I guess thank you. So yeah, I did indeed say that. And so the deep space quantum link, again, this is the physics experiment that we want to do, the fundamental physics experiment we want to do with those long range links. If you just count seconds for sending a pulse of light between the moon and the Earth, it's about 1.3 seconds, right? And the human reaction time to make a decision, they you know, the values vary, but they say about a quarter of a second. So in the transit time of light between the Earth and the moon, there's plenty of time for an astronaut to make a decision. I'm sure an astronaut can make a decision a lot faster than I could. And so the idea is you create an entangled photon pair, let's say halfway between the Earth and the moon. One of those photons goes to ISS, which is staffed. The other photon pair, let's say, goes to Lunar Gateway, okay, which has crew on board. After the creation event, the astronaut can, those two astronauts can each come up with a random choice. They can make a decision about how to measure that incoming particle. But the important thing is the decision is made after the particle is created, and the decision is made by a being possessed of free will. The human presumably has free will, as opposed to a pseudo-random number generator in a computer or some other natural process. And by bringing the human being into play, we introduce freedom of choice, and we break one of the loopholes of the Bell measurement. It gets pretty deep and pretty hairy pretty quick, but there's a lot of good reading if you go in that direction. Bravo for asking that question.
Okay. There was a question for Cass around what temperature are you hoping to get down to?
Sure. So the hope was to get to below 100 picokelvin, which I mean, certainly my hope was to actually get real sort of thermodynamic temperatures below that, and we haven't really hit that yet. In principle, it can be done. The lowest temperature that's been seen on the Earth, last I checked, is about 500 picokelvin. So we would definitely set a record if we can do that. You know, like I mentioned in my presentation, the approach that we were trying to take with this quasi-adiabatic thing is hampered by these background fields that seem to be there. We're hoping in the new system that's been upgraded, we haven't been able to check that yet, maybe a little bit better, we can explore some different compensations. So we'll see. That I don't want to give up on that yet, but it looks harder than I was initially hoping. But there is this other approach, rather than trying to do everything slow, where you basically turn the trap off quickly and let the atoms expand, and then turn the magnetic fields back on in a calibrated way to just sort of bring the atoms to rest, which is sort of effectively doing a similar thing, but more quickly, and that's actually less sensitive to background fields. So kind of hopeful that'll work better. They saw some good results from that in the first SM2 module, the previous one. But they also, there's this issue right now because of the background field, like once you're done and you want to look and see how fast the atoms are expanding, you run into this problem that the magnetic gradients are accelerating them away, so you can't really tell. We know how to sort of fix that. Actually, David actually did these experiments. What he showed, they put the atoms into a non-magnetic state, so that they ignored the background field. So we just have to put all that together with sort of the careful, you know, state preparation that gives you very, very low expansions, and together with putting them into the non-magnetic state. I think that hitting that 100 picokelvin number is definitely still on the table. So we're going to be trying for that in the next few months.
So as a follow-up question, somebody asked, would the ability to sustain a BEC improve if you got further from the Earth?
No, not really. The limit, the basic limit on staying in the BEC is this vacuum pressure problem. Like, even, it's ironic, right? We're up there in space, but then we're in a vacuum chamber in an Earth atmosphere. So, and the vacuum pressure is only so good in there. Actually, the technology to make these sort of small systems with very good vacuum pressure is, you know, limited, and we're working on that. I actually, in reference to that previous question, that we've measured if you don't let the atoms go, if you sort of hold on to them very, very weakly but keep a hold of them, we can keep them for about 5 seconds or so. So that's sort of the time limit that we're up against in the current apparatus. And that won't change. It'd be the same on the Earth or, you know, on the moon or anywhere. It's just set by the vacuum quality inside our system.
Okay. I think we've got time for one more question, unless the organizers tell me otherwise. This is another one for Makan about the what are the near-term opportunities that might arise from advanced space-based quantum optical systems?
Sure. So the main advantage for technology would be to extend the range of quantum communications networks. In fiber, there's loss. In fiber optic, that's like exponent of length. Whereas free space, the loss is 1 over distance squared. And so as you make those distances longer and longer, eventually the free space link has less loss than the fiber channel. And so that's why going to space is really right now the only way we could connect very distant quantum communication networks together. So that's the advantage space is going to bring.
Okay. So I think we are, let me just take here getting.
Ken, thank you very much.
Okay.
Panelists, this has been great, fascinating. I had nothing like any of this in my college courses. This is remarkable. So I thank you very much. And I personally really enjoyed it. If
Thanks, everyone.
Means anything. So now we're going to take a little break until 14:15 UTC, or remembering the subtraction, until 10:15 Eastern Time, when we'll convene for our next panel, Nurturing the Growing Space Economy. Same log in, same everything you did to get into this session, but we will begin at 10:15. Thank you all very, very much.